Howdy class. Today we're going to go over sets and counting. Before we get into the meat of the subject, let's go over the definition of a set. A set is a well-defined collection of objects called elements. Right? Now, the way we communicate what's in these sets we have two big ways. One is the roster notation, and the other one is called the set builder notation. So first, the roster notation, which is a simple list of all the objects in the set. So we have two examples here, A and then B. Set A consists of 3 letters, A, B, C. B consists of 5 letters, B, C, D, E, F, as you see here. And what could be in the set could be, colors, they could be numbers, or any number of different things that you can think of. Now the other one, the set builder notation, this is a rule that defines the property of the set. Like so. So when you look at this example, A equals X such that X is a positive even number less than 11. Basically, all the even numbers 2, 4, 6, 8, 10 is what that would generate. But note how we just use a rule to describe what that is. And again, this part right here, this line, a lot of times you'll see it shortened as to be ST, and so that simply means such that. So again, it's read X such that X is a positive even number less than 11. Alright, so the next, we have two sets are equal if they have the same elements. So in our example right here, suppose set A is X such that X is a vowel in the English alphabet. And then B equals A, E, I, O, U. Well, since they both, one set is done with set builder notation, the other one's with roster notation, but note they both describe the same letters. And so since they all have the same elements or objects, A equals B. Okay, now let's talk about subsets. So basically, if every element in one set of A is also present in another set B, then A is a subset of the set B. So for example, we've got this one here, A equals red and blue, and then B is X such that X is a primary color. So note that all the elements in A are present in B, so we use that to describe that A is a subset of B. We have this next postulate right here. Two sets are equal if, and only if, they are subsets of each other. Alright, so basically what that means is that if A is a subset of B and B is a subset of A, right, they are subsets of each other, then A equals B, if and only if. And we would say arrow going both ways for the if and only if. So let's look at all the subsets of this set A, where A is A, B, C. So first subset is all of them. Right, that would be one of our subsets. Another subset would be where we just contain two of them, AB, AC, and BC. and then each individual letter, A, B, C. Of course, those will be subsets. And then the last one will be a subset of everything, the empty set, which we write as simply a bracket with nothing in it, because it's the empty set. All right, so the exact opposite of the empty set is the universal set. It's the set of all elements that are of interest to whatever it is we're doing. So let's look at these Venn diagrams. A Venn diagram, as it says here, is simply a visual representation of the sets. So note on this first one here, A and B cover all the same information. So this is the case where A equals B. Right here, note that B is a subset of A. Like so. Alright, so for these next two, notice that A here is not, has got parts that are not in B, and B is parts that are not in A, right? A is not a subset of B. And note the same thing here. Clearly, A and B, they're not subsets of each other there either. So A is not a subset of B, and B is not a subset of A. So also note that right here, between those two spots, this is what we call the intersection of B. Over here we have what's called disjoint. And the intersection between these two would in fact be the empty set. Alright, so let's go ahead and talk about the union and the intersection of sets, now that we've already gone a little bit into that. Union is a set of all elements belonging to either A or B. So when we write this, put our bracket, and we'll just use the rule. X is such that X is an element of A, or X is an element of B. Now when you see the word or in math, it's an inclusive or, which means it can be only in A, only in B, or it could be both. Here I'm just going to say it explicitly, or both. Close the bracket. And now when we look at the intersection as a set of all elements belonging to both A and B, right? It's got to be in both of them. So in our mathematical notation, we would say X such that X is an element of A and X is an element of B. Close bracket. Okay. And so now we talk about the complement of a set. And so these are all elements of the universal set that are not a part. We got a little bit of a typo here. Not a part of, not the universal set. It should say the set A. Right, if A is what we're talking about. So a complement would be X such that X is an element of the universal set and X is not an element, let me redraw that, not an element of A. So A complement would simply be everything in my yellow highlighter right here. Okay. So a few notes on set completion. The complement of the universal set, as a reminder, the universal set is everything. And so when you take the opposite of that, what do you have? You have the empty set. You have nothing. All right, and so for this next one, the complement of the complement. So AC is out here, and then the complement of the complement is simply A itself. All right, the complement of everything out here is everything in there. Alright, so we have the A complement, which we'll highlight in yellow here. And then A is already highlighted in blue. You add those two together, you have the universal set. Okay. So here we've got the A complement and A. Where do they intersect? Well, that's where the border between the two sets, but they do not overlap. So the intersection of those two sets is simply the empty set, right? It's nothing, right? Because by very definition, the intersection of A complement and A cannot share any of the same points. Okay, now let's look at properties of set operators. So first one, we've got A union B. All right, well that's just everything in A and then everything in B. And if you reverse those, you still get the same thing, right? So A union B is the same thing as B union A. And then over here, A intersect B is here. And if you say, well, what about B intersect A? Refers to exactly the same thing. So moving on. All right, so here we're going to look at this next set. This is called the associative law for unions. Here we've got A. And then when you look at the next part, B union C, well that's all this right here. And keep in mind it's the union between these two that I've highlighted, not the green, like everything. So this is going to be referring to everything that you see here. And when we do it the other way, write A union B. All right, that's all that right there. And then for C, which is all of this here, again, we're unioning, but we're not looking for the intersection at any point. And so everything there, right? So left-hand side equals right-hand side. Awesome. Now here we have the associative law for intersections. So look at just A here. That part there. And then B intersect C is going to be this guy right here. And so ultimately what we're looking at is this green that is highlighted here. Right, and so that's the set we're looking at. that's being described by the left-hand side of the equation. Now the right-hand side, A intersect B, will be that guy there. And then set C where the green is where they overlap. So again, on the right-hand side of the equation, we're talking about this data set right there. So in both cases, they describe the same thing. And again, this is the associative law for intersections. Next, we look at this setup here where we have A and then B intersects C. Will be this one right here. And we're looking at the union between these two sets. Which is everything that has been highlighted. Okay. Over here, right, we're just redistributing everything A union B in yellow. And then we got A union C. And we're looking at the intersection of these, which is the green right here. And so you see they both describe the same set, therefore they are equal. Next one, we have this guy here. We have A. And then look at B union C. They're very similar to the one we did before, but the intersections and unions are pretty much reversed. And you are looking for the intersection of these two highlighted sets, which is everything you see in green right here. Okay, and so the right-hand side of the equation, we look at A intersect B. And then we look at A intersect C. And we are looking at the union of everything that we've highlighted here. Which is that right there. Left-hand side of the equation equals the right-hand side of the equation. Okay, and so those were just some useful equalities. We're going to look at a few more with De Morgan's laws. So note that the complement basically is distributive, is what this is saying. So left-hand side of the equation, A union B, so that's everything here, and it's a complement. So essentially everything you see highlighted in yellow. All right, now we're going to look at A complement. So basically everything, not basically, it is everything outside of A. Now let's look at B complement. B complement is everything outside of B. And there is a typo on the handout. Let's go ahead and fix that one. This right here should be a intersect symbol, not a union symbol. So make sure you correct that. So when you look at the intersection points, right, that's everywhere you see here in green. And so, which matches what we have with the left-hand side of the equation. All right, so let's move on to the second of De Morgan's laws. Again, another typo. This should say union, not intersection. So make sure you correct that. All right, so the intersection of A and B, and it's the complement of that, so it's everything outside. And then we go to A complement on the right-hand side of the equation. And then B complement. And when you take the union of this, right, which is everything, basically you see that they are equal to each other. So that's all for this video, 6.1, on sets and Venn diagrams and unions and intersections and all the different kind of operations that we do with sets. To the next time, we'll be going over counting the elements, 6.2.